Today I will try to explain the maths behind the line SDF function. And SDF is just a short form of sign distance function, which returns the sign distance, so positive or negative, from our specified point to our specified shape. In our case, it will be a line segment. Alright, so let's say we have our point A sitting at 0, 0. Then we have our point B sitting at, let's say, 2, 0. And we have our line segment from point A to point B. So let me just color it like this. Now let's say we have our point P sitting at, let's say, 1, 1. Let's color it like this. Now what we want is we need to find the closest distance from this point to the point on the line segment. So just by looking at it, I can tell that the nearest point will be this point, so we need this distance. But CPUs and GPUs are not yet smart enough to solve the problem just at a glance, so we need to use some maths. And now to calculate the closest distance from the point P, I will need a vector that points from A to P. So P minus A. And let's just visualize our AP vector. So I'll go AP equals vector. Now obviously I need 2 points to display the vector here, but you can just ignore, okay? A and AP. So I have this AP vector. Now I will get another vector that points from A to point B, which will be B minus A. Now let's also visualize that vector. So AP equals vector of A and AP. So we have this vector. Let's just make it like this. And now here I will project the AP vector on top of the AB vector. And it's simple enough. I can simply go projected vector equals, I need to project AP on AB, so I'll go AB multiply dot, okay, we don't have dots, don't worry, let's go dot product of AP and AB divide by squared length of AB. So again, dot of AB AB. Now obviously I need to define the dot function here. So first I will make some room so I won't be in a way, and then I'll go dot, which will take 2 input, let's say A and B, equals A dot X into B dot X plus A dot Y into B dot Y. And let's visualize our projected vector as well. So I'll go PV equals vector A and PV. So our projected vector will look like this. Now I will simply create a vector that points from this AP vector to our projected vector, which is easy enough. So let's go distance vector dv equals our projected vector minus our AP vector. And let's also visualize that. So I'll go dv equals vector of A and dv let's make it dotted and green. Okay, so I will have a vector that has a direction and a length, and what this vector tells me is if I were to be on this point P, and if I were to move in this dv direction, I will end up on the closest point on this line segment AB. So let's also visualize that as well. So I'll go DL, let's say, for distance line. Let's go segment, and I'll start from P, and I'll go in P plus dv direction, and let's enable the length so we can see. So now we will get the length of the closest point on this line segment from our point P, and it will work amazingly. Now let me get off this extra visualization vector so we can actually see what is going on. Okay, let's keep the projected vector on. So now I will have a closest distance from this point to my line segment, which will be 1.207. But there's one catch here. If my point is, let's say, sitting at here, then I will get the distance to this point, which is not on this line segment. So let's again visualize this AP. So in this case, what I want is I want the length of this AP vector, but we have our projected vector that points in the opposite direction of AB vector. So in this case, I want to make sure that this projected vector's length will be 0, which is easy enough. You can see that I'm using dot product of AP and AB. So if the angle between these two vectors is more than 90 degrees, this value will be negative. So this entire thing will be negative. So I just need to make sure that if this value is negative, simply clamp it to 0. So I'll go max of 0 and the entire thing. So now my projected vector itself will be 0, 0. So I will get the distance from my point to this point A. And on the segment, it will work just fine again. And let's again hide this AP vector. And now let's say if my point is sitting here, then again, my projected vector is going beyond the AB vector. I don't want that, so I need to make sure that this projected vector never exceed this AB vector, which is also easy enough. But in this case, this calculation will return value that will be beyond 1. So again, I'll just clamp it to never exceed 1. So I'll go minimum of 1 and the entire thing, and then I'll get the distance, the correct distance. So this is the math behind the line SDF function. Now I know it looks scary because of this, but you can ignore all this visualization stuff. The actual code will be 4 or 5 lines, like 1, 2, 3, and 4. All right, now let's head over to Shader Toy so we can actually see the code itself. Yeah, okay, never mind. Okay, let's go new shader. I'll just adjust some stuff here. Let's visualize our UV. So currently my UV is 0, 0 here, and it goes to 1, 1 here. So first I want the UV to have the origin in the middle and go from -1 to 1. So I'll simply go 2 into frag coordinates minus my resolution, divide by I resolution dot y. Oops, I just misplaced the decimal point. So now I have origin 0, 0 in the middle, and my y component will go from -1 to 1, but the x component could go beyond that range because I'm compensating here for the aspect ratio. Alright, now let's make our line SDF function, which will return a float value, line SDF, and it will take 3 parameters, vector to point, then vector to A, which will be the first point of our line segment and the second point of our line segment. Now here I need a vector that points from A to P, so I'll go back to AP equals P minus A. Then I need another vector that points from A to B, so I'll go B minus A. Now I will simply project the AP vector on AB vector. So first I will calculate the step value H, which will be dot product of AP and AB divided by squared length of AB, so dot product of AB. And obviously I need to clamp it so it won't go beyond 0 and 1, so clamp 0 and 1. Now I will create a projected vector PV, which will be AB into H. And then we can simply return the length of a vector that points from AP to PV, so PV minus AP. Okay, let's compile. And here, let's call this function. So float line equals line SDF, and the point will be our UV itself. And the line will go from, let's say, -0.5 to +0.5. Now let's visualize our line instead. And I can actually cut out a nice line from this, so I can go smooth step, so 0.01, 0, and our distance. So there we have a nice line segment that goes from -0.5.5 to +0.5.5. Now if I don't clamp this, then I will simply get the distance from my given point to the line or infinite line that passes from point A and point B. Now let's compile, and there we have an infinite line. But we need line segment, hence we need to clamp it. Now this PV vector, I can simply write it like this to get rid of one extra line, and that's the same thing. Now if you look at Inigo Quile's code, he calculates this to vector. So he basically goes vector that points from point P to point A and point B to point A. So it will be just like A minus P and A minus B, just like this. And so if you decide to go this route, this calculation won't be changed, but I need to flip this like this. And that's the same thing, okay? That I've chosen to make this vector point from A to P and A to B because I thought it would be easier to explain and visualize. Alright, that's it. I hope you liked this explanation. And now you should go and check out my thunderstorm shader video for Unit 6, and I'll catch you there.